Hi everyone, I am Dr. Bharat from Department of Mechanical Engineering, Global Academy of Technology, Bangalore. Right now, I am in front of you to talk about analysis of beams using finite element analysis and how stiffness matrix of beam element is derived. Let's begin with the session. The concepts were taken from the book titled Finite Element Method by Daryl Logan. So let's get started. So what exactly are the beams? Beams are structural members that can take transverse loads. Unlike bars, which can take only axial loads, beams can handle shear force as well as bending moments. As a result, there will be transverse displacements and rotation, or here we call it as slope, at every point of the beam. Here the figure shows a beam of length L in global coordinate system. The following notations will be used throughout the sessions. The transverse nodal displacements is denoted by Vi, which will be in y direction, and the rotations or the slope will be denoted by pi I. Also, the shear forces will be denoted by Fiy, and the bending moments will be denoted by Mi. Here I talks about the node number. So these are the following notations which we'll be trying to use throughout the entire session. Okay, where it has a transverse displacement Vi, the slope is noted by pi I. Fi y will be used for shear force, as well as M will be used for the bending moment. Let us understand these notations in detail. Now consider the beam element with two nodes as shown in this figure. Okay. Now this element will have 2 degrees of freedom at each node. That is, the element will have two unknowns at each node. They are the transverse displacement, which will be in y direction, which we call it as V, as well as the slope at each node. Obviously it is denoted by M. So if you can observe here, there will be two unknowns at each node. Since the beam element has two nodes, there will be total 4 unknowns, and these unknowns are also called as field variables. So here there are 4 unknowns in this case. The field variables V1 and pi1, which denotes the transverse displacement as well as the slope at node 1, as well as V2 and pi2, that denotes the transverse displacement and the slope at node 2. Similarly, the forces, the 4 different types of forces which we will be considering, 2 at each node. One is the shear force and the bending moment at node 1, and the second one, shear force and bending moment at node 2. So F1y, 1 exclusively denotes here the force is at node 1, and 2 in this case denotes the force is at node 2. That is how we will be trying to denote the bending moments. So these are the notations which we will be using throughout this entire session. Many theories that describe the behavior of beams under different loading conditions are available, but two theories are frequently used. They are Euler-Bernoulli beam theory, derived by Euler as well as Bernoulli, and second one, Timoshenko beam theory. Euler-Bernoulli beam theory considers that the plane sections remain plane even after bending, but Timoshenko beam theory considers that there will be a shear deformation in the planes after bending. This is a fine difference, obviously a very small difference between these two theories, but in this entire session, to derive the stiffness matrix of beam elements, we will be considering Euler-Bernoulli equation beam theory, and we'll be studying quite about this theory itself. Euler's theory holds good for the beams which deform in elastic limits. The theory comes with certain assumptions. The cross-section remains perpendicular even after bending, and the plane section remains plane without any shear deformations. These assumptions hold good when there is a pure couple or constant bending moment in the beam. But still, the governing equation obtained by this theory was very much successful in predicting the behavior of the beams accurately in many practical situations. So, even though this theory comes with many assumptions, this theory was successfully employed in predicting the behavior of the beams. Let us see this theory. The sign conventions according to this theory are represented in this figure. Now, the shear forces which are in positive y direction, are considered as positive, and the moments and rotations which are in clockwise directions, counterclockwise directions, are considered as positive. So if there is any moment in clockwise direction, if you see here this moment in clockwise direction, this is considered as a negative moment, and the moment or the slope in counterclockwise direction is considered as positive. Similarly, the shear force, if it is moving upwards towards if it is directing in positive y direction, it is considered as a positive shear force, and if it is coming down in negative y direction, it is considered as the negative shear force. So according to this Euler's theory, the governing differential equation for beams having nodal shear forces and moments is a fourth order differential equation given by EI multiplied by d power 4 V by dx power 4, where V is the transverse displacement in y direction. Similarly, according to this theory, the shear force is given by third order differential equation, and the bending moment is given by second order differential equation. If you differentiate the transverse displacement up to third level, obviously you will be ending up by obtaining the shear force. Similarly, you will be ending up in obtaining bending moment if the transverse displacement is differentiated twice. Okay, and obviously this will be the equations which we will be using to determine the stiffness matrices as well as the shape functions. Let us start our work. How do we derive a stiffness matrix of beam element based on Euler-Bernoulli beam theory? Consider a beam as shown in the figure. Let the length of the beam be length L. Okay, it has got two nodes, node 1 and node 2, and V1 and V2 are the displacements, transverse displacement at node 1 and node 2, and M1 and M2 be the slopes at node 1 and node 2. A proper interpolation model has to be selected to define as well as to predict the behavior of this beam element. Now in this case, if you see, a cubic equation was selected, V of x, the transfer displacement, a cubic equation is selected, which is of the form a0 plus a1x plus a2x square plus a3x cube. There are many reasons for selecting such a cubic polynomial equation. First being, now if you clearly observe this beam, the beam element has got totally 4 unknowns. The beam element here has got 4 unknowns, 2 at node 1 and 2 at node 2. Now similarly, if you observe this equation, polynomial equation, it has got 4 coefficients. The basic rule in FEA or in selecting interpolation function is the number of coefficients should be equal to the number of unknowns. So by applying to this rule, I have selected a equation, a cubic equation, a0 plus a1x plus a2x square plus a3x cube, which has got 4 coefficients, a0, a1, a2 and a3, that corresponds to the number of unknowns to this of the beam. And the other reasons being, this cubic equation exactly satisfies the fourth order differential equation, because according to this theory, the fourth order differential equation should be equal to 0 if you differentiate this v of x to the power of 4 for 4 times. Obviously will end up in equating to 0. That is one of the reason why we have selected this cubic equation. Now coming back to the slope. The slope is the first order differentiation of transverse displacement, which is given by pi of x is equal to dv by dx. Differentiate the transverse displacement with respect to x. So once you differentiate it, so here the differentiation of v of x goes here, pi of x, which is equal to a1 plus 2a2x plus 3a3 x square. These are the two equations which we will be constantly using it. And once our work to find in this stiffness matrix is to find the coefficients a0, a1, a2 as well as a3. These coefficients can be found by applying boundary conditions. Now what exactly are these boundary conditions for this beam element? Now if you clearly observe this structure at node 1, okay, the value of x, the x-axis, obviously the value of x is 0. That is what we have written. At x is equal to 0, the transverse displacement is v1. So substituting these values, x is equal to 0 and v of x is equal to v1 in equation 1, v of x is equal to a0 plus a1 into 0 plus a2 into 0, a3 into 0. So ultimately it results in the value of a0 is equal to 0. First coefficient we have already found. So a0 is equal to v1. Similarly, if the same boundary conditions is applied to the slope pi of x, which is equal to, if you can observe, pi of x is equal to pi 1. So pi of x is equal to a1 plus 2a2 into 0 plus 3a3 into 0, which results in a1 is equal to pi 1. So already we have found the two coefficients a0 as well as a1. Let us move forward to find the coefficients a2 as well as. If you want to find the coefficients a2 and a3, we need to once again consider the boundary conditions at node 2. Now say this beam of length L. At node 2, the value of x is equal to L. So the v of x, the value of v of x will be v2. Now wherever we have x coordinate, that coordinate will be substituted in the form of L. So v2 is equal to a0 plus a1L plus a2L square plus a3L cube. Since we have already found that the value of a0 is equal to v1, we have directly substituted a0 as v1, and we have already found a value of a1 as pi 1. We have substituted a1 as pi 1. So v2 goes something like this: v1 plus pi 1L, instead of a1 we have got pi 1, plus a2L square plus a3L cube. Now small mathematical simplification, we have taken v1 as well as pi 1L to the left hand side. So it is how it looks like this: v2 minus v1 minus pi 1L is equal to the other part of the equation, a2 L square plus a3L cube. Similarly, this boundary condition at node 2, that is at x is equal to L, is applied for the slope equation also. So pi of x at node 2, the slope is pi 2. So pi of x is equal to pi 2, whose value will be equal to a1 plus 2a2L plus 3a3L square. So similarly, we are substituting back the value of a1, which we have already found, whose value is pi 1. 2a2L as it is, we are keeping the other equations, plus 3a3L square. Taking the terms pi 2 and pi 1 to the left hand side, pi 2 minus pi 1 will be equal to 2a2L plus 3a3L square. So solving this equation number 3 and equation number 4 will help us in getting the values of the coefficients a2 as well as a3. So these are the two equations which we are going to use. Now this equations, solving these equations, equation number 3 as well as equation number 4, we will be able to find the values of a2 as well as a3, and I am giving these equations directly what will be the value of a2 as well as a3. Now you need to understand clearly here, the solution for obtaining the values of a2 and a3 are clearly given in the slides 19, 20 and 21, which is not discussed in this session, but you can refer the slides in the same session, in the same topic. Go through the slides 90, 20 and 21 for finding the solution of A2 as well as A3. So this process is quite lengthy, so I have given in the slides the process obtaining the solution. So here we have found the values of A0, A1, A2 and A3. A2 value is 3 by L square into V2 minus V1 minus 1 by L multiplied by 2 pi 1 plus pi 2. Similarly, A3 is equal to 2 by L cube V1 minus V2 plus 1 by L square plus multiplied by pi 1 and pi 2. Try to understand. Once again I repeat here. Here A1, A0, A1, A2 and A3 are the coefficients of the transverse displacement equation. L is the length of the beam. V1 and V2 are the transverse displacements at node 1 as well as node 2 in y direction. Pi 1 and pi 2 are the slopes at node 1 and node 2. So substituting these values, this is the equations. A0 is equal to V1, A1 is equal to pi 1, A2 value and A3 value. Substituting this, all the four coefficients in v of x will end up in a equation number 5, which is shown here. This equation is the transverse displacement equation for a beam element having two nodes subjected to a shear force as well as bending moment at the nodes. So this is the equation which governing differential equation which we will be using to derive the stiffness matrix. Now let us understand the forces in this beam in more detail. The force vectors, okay, for the beams is shown in the screen. There will be totally four forces, two shear forces at node 1 and two moments at two shear forces, one at each node and two moments, one at each node. F1y corresponds to the shear force at node 1 in y direction. Similarly, F2y corresponds to the shear force at node 2 in y direction. Similarly, M1 and M2 corresponds to the bending moments at node 1 as well as at node 2. Now try to understand this equations. As per these equations we have got purely from Euler's beam theory. Okay, and F1y is given by the equation E multiplied by I, where E corresponds to Young's modulus. I talks about moment of inertia. It is a third order differential equation, d cube v by dx cube. Now, and since it is at node 1, the value of x is equal to 0. Similarly, the bending moment at node 1 is equal to ei negative of ei d square v by dx square, and since the bending moment is also at node 1, the value of x at this node 1 is equal to 0. One thing you need to clearly understand: the negative sign here, the importance of negative sign. Here the bending moment at node 1 is considered negative because there is a clockwise bending moment. We have considered initially as clockwise bending moment, so it is considered as negative. Similarly, shear force at node 2 is taken as negative value because it is moving against the y direction, it is moving opposite the y direction. At the same time, try to understand here, concentrate here. At node 2, the value of x is equal to L. So at x is equal to L, F2y is equal to minus ei d cube v by dx cube. Similarly, value of M2, the bending moment at node 2 is equal to ei d square v by dx square, and at node 2 the value of x is equal to L, and the value, the bending moment here is positive because it makes a counterclockwise bending moment. So we will be trying to find the values of these forces, okay, by differentiating the displacement equation, transverse displacement equation. This equation we have obtained by substituting, after substituting the coefficients A0, A1, A2 as well as A3. Now these are the equations, equation number 5, which we call as differential equation. Now this equation, governing equation, is differentiated at each stage. So here we go, dv by dx first order differentiation. Since v1 is constant, it ends up in 0 here. You do not have any v1 value here. And pi 1, since we have got x as a constant, it will leave it only with pi 1. And since we have got x square, it will end up with first order differentiation 2x. And here we have got x cube, so it will end up with 3x square. This is the differentiation. Remaining things will be constant and will be as it is. Now differentiating this dv by dx, once again, d square v by dx square. Since pi 1 is a constant, you don't see any pi 1 value here, pi 1 term here. Now here, since we have got constant of x, you don't see a constant x here. It will be only left over with 2, and we have got x square. So we have got, instead of x square, 3x square, we will be having x, and 2x will be there, whose value will be 6. This is how we have differentiated. The differentiation goes on. And third order, because the shear force is a third order differential equation. To obtain a shear force, we need to derive this once again, differentiate this once again. So differentiating this, so since the entire term in this case is a constant, this entire term is a constant, you don't see any value. This term will directly be 0. And since it has got an x term, we will get this value directly here. This will be the value of d cube v by dx cube. So we'll be using these values to find the forces in structure law. So dv by dx, d square of v by dx square, this value will be used to find the bending moment. D cube v by dx cube will be used to find the shear forces. So let us try to find the shear force at node 1. The shear force at node 1 is given by EI d cube v by dx cube at the value of at x is equal to 0. Okay, d cube v by dx cube, the value f1y, once you have substituted the value d cube v by dx cube has been taken from the previous equation. Okay, now here we'll be substituting the value as it is. We have got EI multiplied by 6, 2 L cube, 2 by L cube, v1 minus v2 plus 1 by L square, pi 1 plus pi 2. This is the equation which we have got a value of f1y. Okay, now substituting this value and slightly simplifying here will end up in equation number 6. Now try to once again I explain. The 6 goes inside on 12 by L cube v1 minus v2 plus 6 by L square pi 1 plus pi 2, which once again we have taken L cube common here. Once L cube 1 divided by L cube has been taken out, now it will be left with 12 v1 minus 12 v2 plus we have got 6 L square. Once we have taken L cube out, it will be left with 6L multiplied by pi 1 plus 6L pi 2. These are the equations which you will be getting this. Now here small change which we will be trying to do here. Now if you can observe the beam has two nodes. At node 1 we have got v1 as well as we have got moment. Okay, so v1 we have got at node 1 as well as we have got value of pi 1. I have arranged this equation as node 1 v1 term as well as this is the node 1 and this is also at node 1. First one is transverse displacement and second one is the bending moment. Similarly at node 2 we have got v2 as well as pi 2. We have got pi 2. So here we have got v2 as well as pi 2 in the second equation. This is what exactly small changes in this equations. I have taken node 1 at the initial positions and node 2 as a later positions. We will try to find the value of m1 which is given by this equation as per beam theory. We have already found the value of d square y by dx square. So take this value. This is the value of d square y by dx square. Okay, and we have got the value here. Since x is 0, obviously this value will be there. You can refer these equations. The value of m1 is minus ei multiplied by 2 into 3 by L square v2 minus v1 minus 1 by L 2 pi 1 plus pi 2. A small mathematical simplification where 2 is taken inside, minus 2 is taken inside. Okay, it becomes minus 6 by L square, and v2 minus v1 plus minus 1 by L is multiplied by minus 2, which gives to plus 2 by L multiplied by 2 pi 1 plus pi 2. Similarly, a small equation taking L cube as common, 1 by L cube as common, the equation results, this is the equation which results. On further simplification, open the brackets. This process is very much lengthy, but it makes your procedure very much simple to understand. If you are very good in mathematics, you can be able to write this the final equation, but still remember the process, how the flow goes on. So minus 6L v2 minus into minus goes plus 6L v1 plus 4L square pi 1 plus 2L square pi 2. So here also the same changes which we have done. First we have taken the terms from node 1 which has v1 as well as pi 1, and we have taken the terms from node 2 v2 and pi 2. So here if you can observe, we have found the values of m1 as well as f1 at node 1. Values shear force at node 1 has been found. Now we are going to find the shear force at node 2. See the different common things in these two equations. One is the shear force at node 1 is EI d cube V by dx cube at x is equal to 0. Now at node 2, that is at x is equal to L, it is exactly the inverse of this. The direction is reversed. It is positive here and it is negative. So without doing much efforts, the equation can be, the sign of this equation can be changed here. The sign of the equation has been changed directly here. Okay, EI by L cube is taken directly. Instead of plus 12 V1, we have got minus 12 V1. Instead of plus 6L, we have got minus 6L. Minus 12 became plus 12, and plus 6L became minus 6L. So this is easy when compared to the previous case where we have substituted and we have derived. So this ends up with equation number 8, which gives the shear force at node number 2. Now only we are left with bending moment at node number 2. That is what to find these values. At node 2, x is equal to L and m2 is equal to, given by this equation. Here the positive sign clearly denotes that the bending moment is in counterclockwise direction. Now substituting these values, m2 is equal to, now 2 into 3 by L square. This is the equation which we have got. Wherever we have got x terms, these x terms are changed with respect to L. Now this is where exactly you can find here. Instead of x was supposed to be here. Instead of x, we have got the value of L. Now once again simplifying this equation, EI into 6 by L square, the same terms we are simplifying, the same process we are using, and from here directly we can go through this. I want you to go through this entire equation slowly and carefully. Pause this video, try to understand. This has been written in very clear steps. If you can work out in your notes, it will be easy for you to understand. Now same process which we have done, we have simplified it and taken L cube common, so that all the 4 equations will have one common element, EI by L cube. And also after taking this, we have arranged the terms in such a way that first 2 terms will represent the transverse displacement as well as bending moment at node 1, and the second 2 terms will represent the transverse displacement and bending moment at node 2. So that is how we have found all the force vectors, 2 shear forces and 2 bending moments at node 1 as well as node 2. So arranging this, all the equations 6, 7, 8 and 9 in matrix form. So these are the 4 equations which we have obtained. If once you can see this, EI by L cube is the common thing which we have used, and these are the 4 equations. Equation 1, 2, 3 and 4. Now these equations which we will be trying to use, these are the 4 equations which we will be trying to convert into matrix form. Here we go to convert it. The first 4 equations will be turned here. Okay, f1y, m1, f2y, m2, and EI by L cube will be the common element, and multiplied by the 4 parameters which we are using. V1, pi 1, V2 and pi 2. These are the four things which are common in four equations. So we have got on the right hand side. Now in between the matrix, we got the matrix. Now the same elements, the coefficients of V1, pi 1, V2 and pi 2 will fill this matrix. 12, 6L goes here, minus 12 and 6L. Similarly, 6L, the second row is filled with 6L, 4L square, minus 6L, 2L square. The third row will be filled with minus 12, minus 6L, plus 12, minus 6L. These are the coefficients of V1, pi 1, V2 and pi 2. Similarly, fourth row will be filled with 6L, 2L square, minus 6L, 4L square. So these are the equations which we have got here. Now, this is how we will be trying to convert these equations into matrix form. The matrix so obtained, if you clearly observe this matrix is of the form KQ is equal to F, our governing differential equation in finite element analysis. Now here F corresponds to the force vector, Q corresponds to the unknowns. Now force vector is nothing but F1y, shear force at node 1, M1 bending moment at node 1, F2y shear force at node 2 in y direction, and M2 is the bending moment at node 2. Similarly, Q, this values, the Q corresponds to V1 at transfer displacement at node 1, Q pi 1 bending slope at node 1, V2 transverse displacement at node 2, and pi 2 slope at pi 2. So here we have got the equation F is equal to K into Q, or KQ is equal to F. So the remaining term, what you see here, the remaining term is called as the stiffness matrix. So here we go, that is how we got. So the stiffness matrix is here. This value which you see on the screen is the stiffness matrix, which goes something like this, EI by L cube and the matrix form. This is the stiffness matrix for beam element, which will be used from this point of time for every equation, for solving every beams. This is the common equation, and all the softwares, the computational softwares will be using this equation itself. And at this point of time, this equation we are using it and has been derived based on Euler-Bernoulli beam theory. So this is the process. Try to understand this. If you have any doubts at any point of time, you can refer me, you can mail me, you can ask me at this mail ID. You can put it questions. Obviously I'll be available for you to reply in this, and my next session will be how do we derive the shape functions of the beam element. This slide, obviously, as slide number 19 to 21, as I said, this entire slides consists of the procedure to find the values of A2 as well as A3, the coefficients A2 and A3. Kindly go through this, okay, in this equations. Kindly go through the process, how it is done. Okay, if this you will be able to understand in detail. Okay, hope you have understood. Kindly go back, refer this video, make a notes slowly, understand each equation. If you have any doubts at any point of time, kindly call me back. Thank you. Okay, we'll be meeting in next session with the shape functions of beam element. Thank you very much. Have a good day.